can go live.
Yeah.
Yes, I have clicked it.
Okay. So, so good evening to all attendees across our channels. So I welcome you all to this special series of institute lectures, which are basically organized to highlight the works of Nobel Prize awardees this year. So today's institute lecture will throw light on various aspects related to the climate change and underline the work done by Syukuro Manabe and Klaus Hasselmann, for which they were awarded the Nobel Prize in Physics along with Giorgio Parisi. So we will have one more institute lecture highlighting the work done by Giorgio Parisi on complex systems. So I would like to welcome today's speaker, one of the country's leading expert on climate change, Professor Achyut Rao. On the behalf of the Institute Lecture Series Committee, the faculty fraternity, staff and students of IIT Roorkee, and on my personal behalf, I extend a warm welcome and express sincere thanks for accepting our invitation to deliver this institute lecture, titled Human Influence on Climate. So thank you, Professor Rao. So I would like to proceed with a brief introduction to Professor Achyut Rao. So it's my honor to introduce our speaker, Professor Krishna Achyut Rao. So Professor Achyut Rao hails from Karnataka, and after his graduation in mechanical engineering from BITS Pilani, he went to Tulane University, USA for his master's and subsequently a PhD. After his PhD, Professor Achyut Rao worked as a computer vision specialist, Lightram Corporation. Subsequently, he moved to Lawrence Livermore National Laboratory, USA, where he worked for many years as postdoctoral research scientist and research scientist. He subsequently joined the Center for Atmospheric Sciences, IIT Delhi, as a full-time faculty member, where he is currently the head of the department. Professor Achyut Rao is a member of several national and international committees on climate change. So he has contributed to several IPCC, that is the Intergovernmental Panel on Climate Change reports, as a lead author. Professor Achyut Rao has also served as an invited expert on United Nations Environmental Program Panel. So he's a member of internationally acclaimed climate change working groups, such as HAPPY, which is a half-degree additional warming prognosis and projected impacts, CLIVAR, climate and ocean variability and change, and so on. So apart from these, Professor Achyut Rao has featured on many panel discussions in national media and has also contributed to several columns in the print media. Professor Achyut Rao's primary research interests are regional climate change, weather and climate extremes, climate change detection, attribution, climate risk assessment, and so on. So with this short introduction, I may now request Professor Achyut Rao to kindly deliver his talk. So we will be open to questions. So please type your questions on WebEx chat board, or you can leave them as comments on the YouTube channel. So we will open the talk for discussion at the end. So the floor is yours, Professor Rao.
Thank you so much. Thank you for inviting me to be delivering this lecture at IIT Roorkee. It's a privilege and an honor, and I hope I can do justice to the task ahead of me, which is to place the work of Tsuki Manabi and Klaus Hasselmann in the context of what we know about climate change. It's actually a privilege to do this because this is probably the first physics Nobel Prize. This is the first physics Nobel Prize for climate change work. There has been related to atmospheric sciences a Nobel Prize in chemistry for the work on the ozone hole, and that was from a couple of decades ago. But to recognize climate science for a Nobel Prize is actually quite exciting for me. This is not to belittle the Nobel Peace Prize that the Intergovernmental Panel on Climate Change received, at least a share of it, in 2007. So I will start by sharing my screen and making sure that you can all see my presentation. Okay, is my screen visible?
Yeah, it is.
Okay, Okay, all right. So I'm going to get started right away. I don't have an outline slide because I'm looking at this topic, and the way I'm treating it today is through a meandering lecture, which is hitting many different points in history and in current knowledge. So I'm going to get started without laying that roadmap out for you. Hope you will come along with me in this journey. So the most recent IPCC report, the sixth assessment report that was released a couple of months ago, makes the statement that the recent changes in the climate are widespread, rapid, and intensifying, and unprecedented in thousands of years. So if you look at a figure here that I have shown on the left-hand side of your screen, you can see here the global mean surface temperature. This is going back 2000 years. Some of this data is from proxy reconstructions, and the more recent 150 years plus is through measurements at various locations on the Earth, then synthesized into a global mean. And you can see how the last 150 years have seen a dramatic rise in this temperature, much of it coming in the last 70 years or so, but this is a dramatic increase in temperature, something that is unprecedented in this 2000-year history. In fact, later on, I'll show you how it is unprecedented even going back further. But within this time frame that we have measurements and are able to more precisely know the climate of the Earth, what we in this report have concluded is that when we compare the observations, which are shown in the black line on the right-hand side, with computer model simulations of climate, if we do not include human beings and their activities and how they influence climate, we would have seen almost no change in the last 170 years. This green line here indicates what the climate would have been if it were only natural factors involved. But when you include both natural factors and the effect of human beings on the climate, this brown line that you see, which nearly tracks the observed temperature right across, is what we see. So this is your first hint that this temperature increase that we are seeing, and much of it, like I said, in the last 70 years or so, is likely due to human beings. We are able to actually quantify how much of that change we are caused as human beings. If you look at this gray bar here, this is the observed temperature change compared to the late 19th century, the second half of the 19th century. Our last decade was about 1.1 degrees Celsius warmer. And out of this 1.1 degrees Celsius, the total human influence is about 1.1 degrees Celsius. And of the human influence, if we look only at greenhouse gases, we would have increased temperatures by 1.5 degrees centigrade. But fortunately, along with the greenhouse gases that we emit, we also emit other particulate matter, what we know and understand as air pollution. This air pollution has a cooling effect on our temperatures. So this 1.5 is actually modulated by this cooling effect, ending up with a 1.1 degrees Celsius of human influence. Natural factors, which I will come to and describe what they are, have almost no significance, nor does what we call internal variability. So when we come to the conclusions of this report, it is unequivocal that human influence has warmed the atmosphere, ocean, and land. Widespread and rapid changes in the atmosphere, ocean, and cryosphere and biosphere have occurred. So, how did we conclude this? Okay, this is really the essence of my talk here, is to try and explain how we have come to this conclusion. So, going back to 1757, CO2 has been identified in the atmosphere. And by the 1820s, Joseph Fourier and other scientists have already understood that gases in the atmosphere might trap heat received from the sun. By 1859, John Tyndall suggests that water vapor, CO2, and other radiatively active ingredients of the atmosphere could produce all the mutations of climate which the researchers of geologists reveal. Back then, climate was understood to change, and geologists were the people that had seen those changes. And by 1896, Svante Arrhenius, a Swedish scientist, had published a climate model demonstrating the sensitivity of surface temperature to atmospheric CO2 levels. So this is the earliest time when the fact that CO2 concentrations affect climate was sought to be quantified. By the 1930s, Guy Callender had concluded that fossil fuel burning had been increasing atmospheric CO2 concentrations. And he also made an attempt to update the work done by Arrhenius to quantify how much absorption of radiation is carried out by carbon dioxide and water vapor, etc. So you have here something that's more than 100 years old, where the importance of greenhouse gases were understood. And in 1957, Charles Keeling started measurements of CO2 in Hawaii at the Mauna Loa Observatory. This is a paper from 1960, where the first data showing not just the increasing values of CO2, but also how CO2 has a seasonal cycle in the atmosphere was already known. And closer in time, by the 1970s, various other greenhouse gases had been identified, and also the fact that some of them, like the CFCs, were much, much more effective in trapping heat than carbon dioxide. So how does this understanding work, right? So for the benefit of audience that might not be familiar with this, I'm going to step back and give you some basics here. So we have solar radiation. So at the radius, the mean radius of Earth's orbit around the sun, we receive a certain amount of solar radiation, which we call solar constant, which I'm representing as S0. It's about 1368 watts per meter square. So in further slides, you might see other units. Previously, there were units called Langleys that were used. So now, of course, we have SI units of 1368 watts per meter square. So because we are a sphere, but we are intercepting the radiation as a disk in space, we intercept about S0 times the surface area of the Earth's of the disk with Earth's radius r. And since our surface area is actually 4 pi r squared, the average amount of energy per unit area we receive on Earth is S0 by 4. So this is true of any spherical planet that you know in the solar system. The only thing that changes is the value of the solar constant, which, as you know, as you go further away from the sun, decreases as 1 by r squared, or the distance from the sun squared. So what happens to this amount of energy when it reaches the surface of the Earth is fairly simple to calculate. We rely on radiative equilibrium, where essentially, if you treat the Earth as a black body, the amount of solar radiation we receive is S0 by 4, but a part of that radiation is actually reflected back to space, a fraction that we denote by alpha, which is what we call albedo, right? So this is reflected shortwave radiation. So most of the solar input is in shortwave radiation, and so that's the part that we are looking at. And since the surface has absorbed this 1 minus alpha times S0 by 4, you end up with a surface temperature, which we'll call Ts, and the Earth emits radiation, terrestrial radiation that we call, which is in the long wave part of the spectrum. So this is clearly a temperature dependent thing. Our temperatures on the surface of the Earth are about 288 degrees Kelvin on average. So this balance here between what is absorbed and what is emitted is essentially what dictates our temperature, right? So what we emit at this surface temperature is that sigma T to the 4th from Stefan's law, and that has to be balanced by the solar radiation that's absorbed. So we can calculate what the effective temperature of the Earth is, and this temperature, by plugging in values of albedo, which we think is about 0.3, right? So this is now measured and confirmed, so it's about 0.3. Basically, things like clouds and ice and snow surfaces are the highly reflective surfaces that we have. And oceans are among the most dark or absorbing surfaces that we have. More than 90% of what falls on the ocean is actually absorbed. So if we plug in these values of the Boltzmann constant, etc., you end up with a temperature of 255 Kelvin. Clearly about 33 degrees less than what I told you was the Earth's average temperature of 288. So purely radiative considerations where energy absorbed by the surface and emitted by the surface, if you consider the equilibrium, it would be below freezing point. So what we are missing in this is when you have an atmosphere that actually absorbs the radiation. Okay, so we're going to have a simplistic model here where we are actually going to stick an atmosphere that is completely opaque to the long wave radiation we emit from the ground, but is fully transparent to the short wave radiation that we receive from the sun and reflect back. Okay, so if this is fully opaque, then the radiation we emit from the ground is going to be completely absorbed in this atmosphere, and that atmosphere is going to acquire a certain temperature, which we'll call TA. And what's going to happen is because of that temperature, we're going to radiate a particular long wave of A in all directions. So there's A coming back towards the ground and A going back out to space. So this radiation A is now going to balance at the top of the atmosphere what went through. So this A is equal to what we absorb within the atmosphere surface system. Okay, so what used to be the surface is now top of the atmosphere. So our surface temperature radiates S, that's sigma Ts to the 4, and the atmosphere emits sigma Ta to the power 4. So at the surface now, what we have is what is absorbed from the incoming solar radiation and an additional amount that is now being radiated back from the atmosphere. Okay, so this extra amount A is what pushes our temperature above 255, because this term didn't change. It's still the same amount, but you now have back radiation from the atmosphere that's going to make this temperature above 255. So this is what we call the natural greenhouse effect, the fact that we have an atmosphere that's back radiating towards the surface. So if we calculate the values, we can back out what the atmospheric temperature is. It will turn out to be 255. And from that, when we calculate the value of A and what the surface receives, you end up with a temperature of 303 Kelvin. So clearly 303 is much more than 288, whereas 255 was much less than 288. So in reality, what we have is not a perfectly opaque atmosphere, but a leaky atmosphere, which we call a leaky greenhouse. So essentially, the radiation that's emitted from the ground is not fully absorbed in the atmosphere, but some fraction epsilon is absorbed, and the rest of it is transmitted through the atmosphere. So again, you have these radiation from the atmosphere. This is going to be less than what we had seen in the previous case, but you can once again do the radiation energy balance at the top of the atmosphere and at the surface. So at the surface now, you have the same terms, but a slightly different value of A. And at the top of the atmosphere, you have not only what the atmosphere emits, but the fraction of the surface radiation that is actually leaking through the top of the atmosphere. So you can now use standard equilibrium assumptions, and you can actually come up with a relationship for the surface temperature in relation to the effective temperature, which is 255, and that's at the atmosphere here. So you can see here, if I have a perfectly transparent atmosphere where epsilon would be 0, then my surface temperature is the effective temperature of the planet, which is 255. Now, if I have a perfectly opaque atmosphere, my epsilon would be 1, and I would have a surface temperature, which is 2 raised to the 1/4 time 255, which is 303. So epsilon is something in between 0 and 1, and that's really where we are as a planet, where we have constituents in the atmosphere that absorb not 100%, but some fraction of it. And if we increase those constituents in the atmosphere, the epsilon is going to keep increasing. As you increase epsilon, you're going to end up increasing the surface temperature, right? So this is essentially all of climate change reduced into 3 slides, where you understand that the mechanism for the increasing temperature at the surface is actually quite simple. whatever you put into the atmosphere, if it absorbs long-wave radiation, it is going to increase the surface temperature. Now, clearly, some of it is useful. If there were no absorbing gases, you would be at sub-zero temperatures at 255 Kelvin. So there is a natural greenhouse effect that is important, but what we are doing is increasing this epsilon and therefore enhancing the greenhouse effect. So CO2, as we've already seen, is one of the things that was recognized early as a player in the absorption of long-wave radiation. So this is a history of CO2 going back 60 million years. And this is calculated or measured through various means, including from ice bubbles trapped in, air bubbles trapped in ice cores, etc. So this is going back 800,000 years, where we have a precise measure. And going back even further, we have other proxy data that allows us to infer the concentrations of CO2. So you can see here that the present concentrations of CO2, and I want to point out that this scale is highly nonlinear. These last 100 years or so is in this piece, and this piece is about 1900 years, and then this is 800,000 years, and this is about 59 million years, right? So what we see here today is probably the last time we had such high values of carbon dioxide was going back 2 million years. So this is an important point to keep in mind, that for the longest time, especially in human history, these values have been hovering around about 270, 280 or so. Okay, so this stretch here within the last 2000 years is about 280 parts per million. So this clearly, this increase in CO2 has had some consequences, and these are some of the observed changes in our climate. So this is, again, a similar figure to the one I just showed you, but for global surface temperature. So this portion here is in the last 120 years or so, and you can see how the temperature has changed rapidly since about 1950, and this rate is unprecedented in about 2000 years. So this increase is also comparable to going back, and we don't think we have reached such temperatures anytime in the last 125,000 years, going back to when we had our last time when glaciers were at their minimum, the time that we call interglacial. After that, we've had a period of glaciation, which is what we've been coming out of in this end here, going back more than 10,000 years. The land has warmed much more rapidly than oceans. And we can see here that when you filter this time series and take decadal averages, you can see how each 10-year period has been warmer than any decade going back at least to the 19th century. This pair of figures tells you what the rate of warming has been. This is between 1900 and 1980, and this lower panel is since 1981. So this 40-year period, the trends of temperature change globally, you can see how are much, much more than the rates of change in the 80 years preceding that. So this is an increasing rate of change of temperature that we see here. In addition to temperature, we've also seen how the surface ocean pH has been decreasing. This is basically because as you increase carbon dioxide concentration in the atmosphere, the ocean waters tend to take up and dissolve more of that CO2. And because CO2 dissolved in water produces carbonic acid, the pH has been decreasing. We've also measured changes in the surface area of snow cover covering the northern hemisphere. The month of April is chosen because it is when you are going into spring, when the snow cover starts melting. So it's at a peak just before the melting starts. And this area has been decreasing. The amount of ice in Antarctica and Greenland have been decreasing much more rapidly on Greenland than in Antarctica. So this is the change in mass in gigatons or billions of tons. And this is a huge amount of ice that has been melted since only the 1990s. And because you have melting snow and ice, which ends up running off into the ocean, and I don't have a slide to show you, but the oceans have been absorbing a tremendous amount of heat. In fact, 93% of all the additional heat that is trapped by greenhouse gases is absorbed in the ocean. So there is a thermal expansion of the ocean because of this additional heat and because of this additional water that has been melted from land and has flowed into the ocean. You have additional volume. So both of these end up creating sea level rise, and that sea level rise has been accelerating in recent decades. So the question is that going back in Earth's history, I've showed you how CO2 has changed, how it has varied over time. We've also seen how temperatures have varied over time. And this is all long before us human beings have been emitting CO2 and other greenhouse gases. So the question is, isn't all of this just natural? So let's look at what the natural factors that can influence climate are. So solar radiation, even though I called it a solar constant, is hardly constant. The solar cycles that people might have heard about, the sunspot cycles, indicate that there are solar minima and maxima when you have a lot of sunspots. In fact, there's more radiation leaving the sun than when there are fewer sunspots. So these solar cycles, which go from 11 years to even longer low frequency variations, can affect these output from the sun. But that's about a 1% variation in the overall amount of the solar radiation. Then there are volcanic eruptions, and these volcanic eruptions can put dust into the atmosphere, dust and sulfate aerosols that can be put into the stratosphere, for example, where they can reflect solar radiation. And this reflection of solar radiation is essentially increasing the albedo, if not permanently, at least for a few years while that dust stays in the atmosphere. So for a couple of years after a major volcanic eruption, the Earth's temperature actually cools. In addition to that, our own orbit around the sun is hardly stable. The Earth is wobbling around the sun like a spinning top. It has a ellipticity that can vary with time. Its tilt can vary with time in terms of not just the angle of the tilt. We are currently at 23.5 degrees tilt from the normal, but it has been 22.5 to 24.5 in the past. And because it's spinning like a top, the orientation of the Earth has also changed, and that is something that we call precession. It essentially affects which seasons you get more radiation in which hemisphere, and how the seasons themselves were reversed in the past. So, and then of course, because the Earth is a dynamical system which is highly nonlinear, with many nonlinear processes involved, it has what is called internal variability, where changes can occur just by internal oscillations that are generated from the nonlinearities. And then there are man-made factors, right? So we know we have been able to measure, at least since late 1950s, the CO2 concentration, and this is the famous Keeling curve named after Charles Keeling, whose photograph I showed you before. CO2 has been measured to have increased. In addition to that, other greenhouse gases such as methane, nitrous oxide, CFCs, and ozone, etc., have also been changing in concentration and increasing. We also have many of our activities that involve burning fossil fuels and biomass, which produce aerosol particles. And just like volcanic aerosols, these anthropogenic aerosol particles are also mostly scattering. Some can even absorb solar and long-wave radiation. So they also interfere with the radiation. And then we also modify the land surface. Here is a pair of images from the same region taken about 30 years apart. After deforestation, you can see how the reflectivity of the Earth's surface has been fundamentally changed. So wherever you have deforestation, you have an increasing albedo of the surface. So these three factors actually are the major ways in which anthropogenic activities change the conditions. The bottom two by changing albedo, the greenhouse gases by changing the amount of long-wave radiation our atmosphere absorbs. So ideally, if we were to try and pinpoint a cause to say it is the increasing greenhouse gases, or if it were albedo changes that we are creating that are responsible for the changes in climate, we would have some undisturbed Earth and compare the real Earth that we have, where everybody's got their lights on enough to be seen from space, and all that lighting involves burning fossil fuels in order to produce electricity, right? So these two would be compared in an ideal framework. But since we don't have this undisturbed twin Earth that we can compare things to, we have to resort to climate models. And climate models have been incredibly useful tools in this regard. And this brings me to the pioneer of climate modeling, and that's Tsuki Manabi. So Tsuki Manabi has been at the GFDL, the Geophysical Fluid Dynamics Laboratory in Princeton. He's also faculty at Princeton University. So these are some of the early pictures with the founding director of the GFDL, Joe Smegorinsky. But the seminal paper that Tsuki Manabi is still credited with, and this is the paper from 1967, which was even a few months ago. There was a poll of climate scientists, and they rated this paper as the most influential paper in all of climate science. So let's see what's in this paper. So I talked to you about radiative equilibrium, how the surface temperature can simply be thought of as a radiation balance between Earth and space, and even within the Earth, between the surface and the atmosphere, right? So if you look at the atmosphere has a varying density with height, and you also understand that you can have different amounts of greenhouse gases because denser air will have more of it, and therefore that you don't really have a single layer atmosphere, but ideally a multi-layer atmosphere. And so you can do a radiation balance calculation to figure out what the temperature profile of the Earth's atmosphere is as you go vertically up. So we had been looking at a zero-dimensional model. You can build it into a one-dimensional model with the vertical atmosphere, and you can even enhance your assumptions of a gray body assumption for the atmosphere, etc. But what Manabe showed, and he was not the first to suggest it, that perhaps radiative equilibrium does not explain the vertical temperature structure of the atmosphere. Okay, so here are three curves, two of which assume radiative equilibrium. Basically, every layer of the atmosphere is radiating up and down and absorbing long wave radiation at different amounts. And if you have to account for water vapor, then you can either fix the absolute humidity or the relative humidity. So in either of those cases, when you have radiative equilibrium assumptions, what he found is that the atmosphere, which we are looking at mid to upper troposphere here, going up to about 100 millibar, that the atmosphere is way too cold compared to observations, and you can only fit the observations if you actually assume that it's not just radiative equilibrium, but radiative convective equilibrium. Essentially, radiative equilibrium creates these discontinuities in the temperature, which, as you know, is not a stable condition, and that instability is triggered because of differences in the density, and therefore you have convection. So convection actually performs an important part, and this paper was the first to demonstrate that. So what we have in the atmosphere is actually what we call radiative convective equilibrium. So in addition to the radiative solar heating and the atmospheric back radiation coming to the surface emits radiation, but there's also some part of the surface heat that is lost through evaporation and turbulent sensible heat fluxes. And that heat flux ends up going and heating this troposphere through condensation and the latent heat release. And this we know as our clouds, where the latent heat is released and condensation occurs, and also the sensible heat, the thermals that go up from the surface. So without this additional amount of heat, what you would have is that the surface would be much hotter, the troposphere would be much cooler, leading to unstable conditions. So the first proof of the radiative convective equilibrium comes from this single-dimensional 1D model, what is in atmospheric science called a single column model that Manabe ran for this paper. Now, this paper had two other incredibly important results. The first one, what he did was to vary the solar constant. Okay, so one of the theories of climate change back then was that everything is driven by solar radiation changes, right? So you know that the sun is like a flickering light bulb. So those little variations in the solar constant is what is creating changes in surface temperature. So in that single column model, what he did was vary the amount of solar constant, and this is where you see this Langley's per minute unit. The value is 1.96, but he's changed it to vary it between 1.2 and 2.4. And you can see here, if you increase the solar constant, it heats the entire atmosphere, not just the surface, but the entire column. And if you decrease the solar constant, it's going to cool the entire column, right? So this is what solar radiation variations do to the temperature of the surface atmosphere column. Now, on the other hand, if you do what he did, which is vary the CO2 concentrations. So started with a base CO2 concentration of 300 parts per million. And then he doubled that concentration to 600 and also ran another simulation with half of the concentration, which is 350, right? So what is this figure? Now, this figure is a little hard to read, so I'm going to show you a figure that was put out by the Nobel Committee. And this is what this figure now clearly shows. The black line is your 300 parts per million, red is 600, and blue is 150. So if you look at the surface here, 600 parts per million has a higher temperature of about 2.36 degrees Celsius compared to the 300 parts per million. And the 150 parts per million has about 2.28 degrees C less than the temperature of the 300 parts per million simulation. But if you look at what's going on in the stratosphere actually cools when you have more CO2. While the troposphere has warmed, the stratosphere has cooled when you increase the CO2 concentration. And if you decrease the CO2 concentration, this troposphere surface cools, but the stratosphere warms. Okay, so this is a completely different picture than what the solar radiation variation will give you. So within the atmosphere, you end up with this kind of a difference. So the larger the mixing ratio of carbon dioxide, the warmer the equilibrium temperature at the surface and troposphere, larger the mixing ratio of CO2, the colder the equilibrium temperature of the stratosphere. And the temperature change in the stratosphere is much more than in the troposphere. So this was a seminal result from that paper. Now, how does that stand up today? You have here the radius of the measurements of upper air temperature trends. This gray line here represents the tropopause. You can see here that below the tropopause, you have increasing trends, and above the tropopause, you have cooling trends. And this is looking at global averages, the trends between 1980 and 2019. And in the tropics, you have different radio occultation and other ways of deriving the trends. And you can see here that this holds up even in the tropics. But within the tropics, you have an expansion of the tropics, as well as you have a higher amount of warming that is seen within the tropical troposphere. So this one-dimensional model then went on to become a full atmospheric model with realistic distribution of land. And this is a paper that Manabe and Weatherald wrote in 1975. This is the box diagram of the parts of or the processes that are within this model. And they were running this on a UNIVAC with 0.5 MB of memory. So this is for people to understand that you don't need fancy computers to do great science. Some people have managed to do it with even half a meg of memory, much, much less than anybody's cell phone these days. And this was a supercomputer then. And then Manabe also went on with Kirk Bryan to build what is called a coupled ocean atmosphere model. Kirk Bryan, an oceanographer, put an ocean model together, and now the amount of processes in the atmosphere and in the ocean and how they talk to each other, the sensible and latent heat fluxes from the ocean surface, etc., are there. So although the first single column model results came in 1967, it took a good couple of decades before you could have a fully coupled model, right? A coupled model is important because the ocean, as we've seen already, has an enormous thermal inertia. It's got heat capacity that's much more than land. And therefore, if you don't account for it, you will not be able to account for climate change in a reasonable way. So this is one of the early papers that came out from Manabe and his group. Ron Stoffer was the author in this. And this paper essentially talked about certain characteristics of how climate change patterns are going to evolve, how there's going to be an asymmetry. And what they did, now Stoffer and Manabe revisited their results from the 1989 paper in a paper in Nature a few years ago. And this is this model from 1989, their model results. So you can make out the outlines of continents here, and you can see how they predicted climate change, temperature change to be much more in these regions compared to the rest of the globe. And this is what the observations show 20 years after this model simulation was carried out. So you can see here that the patterns of change, not the values of the temperature change, but the patterns of change are almost identical to what they predicted that long ago. And not just on surface temperature, but this is also how much heating the ocean is going to undergo. So this is the plot from their paper in '89, and this is the observed temperature change in the top 2 kilometers of the ocean. So these early climate models, not just Manabe's, but a whole host of others. There were German groups, there was Jim Hansen's group from NASA GISS, and even Nordhaus, who's won a Nobel Prize for climate change economics. He had a model. So all of these made predictions back in the 70s, and you can see how each line here represents a prediction. And this black line is the observations of temperature change. And you can see how temperature change has followed this pattern. And this is your typical climate model where you back then had very little of the detail. So just being able to track the observed temperature change is not enough, because there's more complications to climate change, how the patterns of change are going to unfold. And this is where the second work by Klaus Hasselmann comes in. And what he did was essentially, even before these climate models were up and running, in the 70s, he was able to build the theoretical framework by which you can understand climate change and quantify. And his basic contribution was to regard the signal and noise characteristics of climate change. So he pointed out that you would not be able to find climate change just based on statistics of individual grid points, but rather you have to do it much more thorough, measured way. So this is the first paper where he developed a stochastic climate model. Essentially, he was able to separate what weather and climate are. Okay, he was able to partition their characteristics, and that these partitioning, essentially weather is stochastic noise, and how that stochastic noise is like a random walk, and that because you have parts of the climate system which are responding to that stochastic noise, they respond in a way that is represented in a different way. So if you look at stochastic noise in this figure, this is an idealized figure, but this is actual measurements. This is 500 millibar temperature in the atmosphere. You can see here that this is almost white noise, that there is across all frequencies, there's a similar power. But if you look at SST, SST has low frequency power that represents a red noise response. So even though the weather has certain characteristics, climate has completely something else. So what you also pointed out was that these characteristics can be separated, and you can actually predict, and you can say that with feedback you can actually have stable climate states, and that the variability is not going to run away. So these feedbacks and things, therefore, are an important part of what climate states are. And a second paper, again, this one was actually a conference paper in an obscure conference. And here he laid out the theoretical basis for actually making the case for a detection of climate change. So what he said was that the patterns of change would be in some ways unique, right? So between different kinds of patterns, you would have to first filter your response, and without the filtering, you wouldn't be able to do it. This is where the grid point statistics being useless comes from. And so this filtering is required because otherwise the number of degrees of freedom is way higher than would be possible to actually statistically show. So much of that filtering, reducing 1,000 to 10,000 degrees of freedom down to about a dozen or so degrees of freedom. So this is the part of the paper that talks about the necessary for filtering, but there's also this part about having different forcings to the climate system, possibly producing different responses. So when you have greenhouse gases versus solar radiation versus something else, these all have different responses in the climate. And so the response, actually, if you are able to rotate the guest response in the noise field in order to give you a better signal to noise ratio, you can actually detect these changes much faster. So I'll give you a couple of quick examples to show how this is done and how this was done in. So the IPCC first assessment report in 1990 actually described this better. It says the detection problem can be described in terms of signal and noise. The signal is the predicted time-dependent climate response to the enhanced greenhouse effect, and noise is any climatic variation that is not because of the enhanced greenhouse effect. Now, detection requires that the signal is large relative to the noise. So this also is that the detected signal should be specific to a particular cause. You cannot have multiple possible causes that are giving you the same response. Okay? So, but then the IPCC 1990 also said we might conclude that detection with high confidence is unlikely to occur before the year 2000. So they were wrong on this part, because by the mid-90s, there were a bunch of papers, Ben Santer, Gabi Hegel, both of whom were postdocs under Klaus Hasselmann, who went on to show that the detection of climate change signals in the Earth's observations. Okay, so by 1995, this statement was made that the balance of evidence suggests a discernible human influence on global climate. So let's look at what some of this was based on. So this is a model simulation of what the vertical structure of the atmosphere. So this is going from north to south, and this is a vertical slice. So going from surface up to the top of the atmosphere here at 10 hectopascals. So this is the pattern of change you will get if you only have greenhouse gases that were changed in a climate model. Okay? And if you include sulfate aerosols only, so sulfate aerosols have a scattering effect on solar radiation, and therefore they cool, so much of the atmosphere cools. If you have stratospheric and tropospheric ozone that are changed in the climate model, tropospheric ozone increases tend to warm the troposphere, whereas in the stratosphere, because of the CFCs, there's been a depletion of ozone that tends to cool the stratosphere. And volcanic aerosols tend to warm the stratosphere but cool the troposphere. And solar irradiance, as Manabe had showed, warms the entire atmosphere. So all the changes that you can have in different aspects that affect the temperature in the atmosphere have very different looking patterns. Okay? Now, if you include all of them, of course, now you can see that there are features from each of these. So you can actually, what you can do is take each of these patterns that a model guesses, basically, right? You put some forcing into a model and it produces a pattern of change. And what you can do is you can look for this pattern of change in the observations. Okay, so let's take a look at this. So this is the pattern of atmospheric temperature changes in up to the mid-90s. Okay, so you had tropospheric warming, and within the stratosphere you have cooling, and more cooling in the southern hemisphere compared to the northern hemisphere because of larger ozone loss here. So if you changed CO2 only, if you only accounted for CO2 increase, this is the pattern of change, which doesn't look quite like this. But then if you include changes in sulfate aerosols and stratospheric ozone, now you have a model simulation that is pretty much like this. The models were deficient in how well they accounted for stratospheric ozone loss, which is why you don't quite replicate this. But otherwise, you can see that the overall structure of temperature change, where the increases due to CO2 have been tempered by sulfate aerosols, is there. And one way of looking at this is also by looking at the tropopause height, right? So where you have tropopause is where the tropospheric temperature, which is decreasing, suddenly starts increasing with height. And this is where your stratosphere is. So this tropopause height actually responds to CO2. As we've seen, the tropospheric temperature increases with more CO2, but the stratospheric temperature cools. So if this was your nominal tropopause height, with increased CO2, you have an increase in tropopause height. Volcanic eruption, on the other hand, what it does is, because there are all these particles in the stratosphere, it absorbs solar radiation, but it cools the troposphere. So in the stratosphere, you have warming, and in the troposphere, you have cooling, and so the tropopause height decreases. Okay, so if you look at how tropopause height has been changing, okay, there are black lines here that show how tropopause height has been changing in time. You can see here that every time there is a volcanic eruption, that tropopause height decreases. But otherwise, because of the steady increase in CO2 concentrations, you have tropopause height actually increasing. But going back to the late 19th century, you see that the CO2 change was very little, and therefore you don't have a trend. But every time a volcanic eruption happened, you had the tropopause height dip. And after a couple of years, when the aerosols fall out, you have it go back to where it was. So the gentle increase in in tropopause height is due to the CO2 increases. So we've also been able to make these, see these warming signals in ocean temperatures, subsurface, etc. So this gives us a picture of how different ocean basins have seen temperature change. How am I doing in terms of time? Is it time to wind up now? Because I could wind up in the next couple of minutes if that's useful.
That should be fine. That should be fine.
Okay. All right. So essentially what we use here are different kinds of model simulations. You've seen how in this figure and in previous figures, you've had only natural forcings where volcanic eruptions and solar radiation variations are there. And then you can have simulations, model simulations, where you include what the human caused changes are in greenhouse gases, aerosols, etc., etc. And it is when you include the human forcings that you actually are able to capture the observed changes. And this is the same case with ocean warming also. So control run, meaning that there is no human or natural forcings. This is how much the natural variability is. But if you include what the human forcings are, then you get this green band of simulated changes, which completely includes the observed changes. So there are various kinds of model simulations, etc., that are required for this. Clearly, if one has to get an accurate representation of noise, because your whole basis is that you're saying that there is a signal which is caused by increases in greenhouse gas or solar variations or whatever it might be. That's your signal. And your signal has to increase over time or the manifestation of that signal has to increase in the observations. But then there are natural variations in climate. You know of variations in climate such as the El Nino Southern Oscillation, or even longer term decadal scale oscillations in climate that are naturally occurring. So any of these changes have to be larger than what we consider noise. So Again, in order to do this, there are various ways to look at long simulations of climate without any forcings. And that's where long control runs of pre-industrial climate are used. We also verify these against paleoclimate data to see that the unforced by various human factors, climate has the right amount of variation that we can gather from proxy data that goes back to millions of years. So all of those natural oscillations have to be captured in magnitude by your climate model. Without that, they don't have an accurate representation of noise. If you have too little noise, then you can convince yourself that your signal is much greater than the noise, and therefore you are able to detect any changes. But in reality, signal is much less. In reality, signal has to be much more than the noise in order for you to conclude that. We also have simulations that include individual forcings, as I have showed, in order to see what the response of the atmospheric temperature or various other things are. You have to have a picture of what that signal is from greenhouse gases. And is it uniquely different from solar variation? As Manabe showed, the fact that solar variations produce a uniform response in the entire temperature column, atmosphere column, but not greenhouse gases. CO2 warms the troposphere and cools the stratosphere, unlike solar variations or unlike volcanic aerosols. So these all have these unique signatures, which are called fingerprints, just like you would have in a murder investigation. The fingerprints are unique to each person, and therefore you can figure out whose fingerprint was where and is that the cause. So all of these kinds of climate model simulations go into being able to decide them. So I'm going to stop here and just inform people that we've, in my group at IIT Delhi, we've used some of these techniques of detection and attribution to look at temperature changes over India. And if you are interested in the details of how these techniques are applied, because going into the nitty-gritties of this will be it will be a separate seminar on its own, and I hope I've been able to convey how we look at different causes, how they seem to have unique patterns of how the climate responds, and how these patterns have been growing over time. I'll stop here and take any questions that you may have. Thank you.
Yeah. Thank you so much for that wonderful lecture. So we have a couple of questions, so I can read them out to you. So Piyush asks that what are the sources of terrestrial radiation?
So any surface which is not at absolute zero is going to radiate, right? So if you have a land surface or an ocean surface or even ice and snow, each of these are going to radiate. And this is long wave radiation that is going to be measured. It can be measured, and all of this is terrestrial radiation. So anything, any surface at all, even plants, leaves, etc., everything is radiating. And if you've looked at, you can look at satellite long wave radiation. You can see how different surfaces are at different temperatures. You can actually look at high clouds, essentially thunderstorm clouds, which go all the way up to the top of the troposphere, where the temperature is very low, and you can identify thunderstorm cells by looking at the radiation signature. The long wave radiation is much lower from high clouds than it would be from a surface. And people use this also to actually measure the temperature of buildings, etc., where if you look at MODIS, for example, you can identify urban areas which are much hotter than surrounding rural areas. So terrestrial radiation is everywhere, every surface.
So this terrestrial radiation is basically the long wave radiation window that is going out, right? So,
Correct.
So do you think, I mean, on a local scale, if this will severely affect the weather during a particular season or during a particular, within a very short frame of time?
Yes, it can. Well, it's not just the radiation alone, but it has been shown that, for example, urban areas where you have more absorbing, more surfaces that are able to absorb solar radiation, for example, that these are at a higher temperature compared to rural areas where there's more greenery, and also because in where you have greenery, whether it's rural or urban, you also, the incoming solar radiation is partitioned into probably more latent heat that you can consume that absorbed solar radiation. So when you have water that evaporates, for example, your surface doesn't heat up as much. So these, garden-like areas and forest areas will have lower temperatures compared to urban areas. And urban areas, therefore, have more long-wave radiation that they produce. And this has been shown to affect weather patterns, at least some of the bigger cities, etc. So I can't talk of single neighborhoods, but cities have been shown to alter the weather patterns over time because as cities expand, the amount of radiation and the amount of heat that is there can actually trigger certain kinds of weather events and can affect local weather. Yes.
So we have another question. Can we expect the role of any natural radioactivity in the Earth's climate change? Has it been an attributing factor in any attribution studies?
When you say natural radiation, natural radioactivity.
Radioactivity.
So radioactivity as in what might be coming from
the naturally occurring
and other fissile material. Actually, the amount of radiation that those produce is not significant enough compared to the amount of energy in, say, short wave from the sun or long wave emitted by the surface. So I don't know of anybody that's explicitly calculated it, but I am sure somebody has done it, but this is a very small contribution to the overall energy that is within the surface atmosphere system. And also, it's a question of wavelengths, right? So, as I mentioned, the greenhouse gases are essentially trapping the long wave radiation, which is infrared. The naturally occurring radioactivity is not releasing as much in infrared, as far as I understand.
Okay, yeah. So we have one more question from Debarshi. So it's if in the radiative equilibrium model, there is an upper limit to the value that epsilon can take, which corresponds to an upper limit of the surface temperature. So what it implies is that, so no matter what humans do, the surface temperatures cannot go above that value. So is that a correct inference?
assuming everything else remains the same. Okay, so if my alpha remains at 0.3, yes, that is correct. I will have an upper limit of 0.3. Now, unfortunately, as you increase temperature, you're going to melt snow and ice, which we have seen, right? Which is actually measured, and I showed you data for that. And when ice and snow melts, the reflective parts of the Earth's surface that make up that albedo of 0.3 decreases. So your albedo decreases. If I were to change the albedo to 0, right? If 100% of what comes from the sun is absorbed, then you have the possibility of much, much higher values of temperature. But, you know, the clouds are not going to actually go away. So there will be clouds, so there will be some albedo, but the ice albedo is going to disappear. But you have to also understand that that is if you have a single layer of perfectly absorbing atmosphere. Okay. Now, if you think of the atmosphere as multiple layers, all of which are opaque, you end up with each layer amplifying it, and you will end up with a surface temperature that is much, much, much higher. Take the example of Venus, for example. Venus has a surface temperature of 475 degrees centigrade. Okay, so this is much higher than what its albedo would tell you. In fact, Venus has an albedo of about 0.7. So a 0.7 albedo with slightly higher solar constant for Venus actually implies an effective radiating temperature of about 221 Kelvin, unlike Earth, which has 255. So 221 Kelvin in Venus is the effective temperature, but it has a surface temperature of 475 centigrade. So it's actually because if you calculate the number of fully opaque layers, you would end up with 19 fully opaque layers in the atmosphere, which would explain how the surface got to be so high. So there is no upper limit. If we keep adding greenhouse gases into the atmosphere, there are feedbacks that will cause ice and snow to melt. The clouds' heights can change. And if you have low clouds, they have a different albedo and greenhouse trapping potential compared to high clouds. Then there are other things such as carbon cycle feedbacks, where carbon that is stored in the oceans and in the land, all of those get released into the atmosphere. So those feedbacks will further add to the climate change. So the simple radiative model is just that. It is just a zeroth order, zero dimensional model that is supposed to understand the basic radiation energy balance with space. But within the atmosphere and surface system, what happens is much, much more complicated than a simple radiative.
Great. So I have got one more question it's my own question. So looking in the context of paleoclimatology, so there have been several incidences of warming and as well as cooling, right?
Yep.
So can't we assume that this increase or this warming will also be substantiated over the period of time, and we would again come back to the normal or the mean temperature if we allow sufficient amount of time to elapse?
Right. So as I mentioned, there are orbital variations, right? The eccentricity changes, and the tilt will change, and the precession of the axis will change. So what those changes have done in the past is that they have produced very minute variations in the amount of solar radiation reaching the Earth. Okay, so all you need is a small decrease in solar radiation, let's say reaching 60-degree north latitude or 60-degree south latitude. When you have just a small decrease, what that will do is that it will make your summers cool enough that you don't melt the ice that and snow that fell in the previous season. Okay, just cool enough. And you have that over a few years. What it's going to do is it's going to build on the snow, and that's going to change the albedo of the planet. And when you increase the albedo of the planet, that is going to further reduce the temperature, which is going to build more snow and ice. So that's how the feedbacks are what take it into an ice age. Okay. And when you get very cold, you also end up reducing the amount of carbon dioxide in the atmosphere, because cold oceans and cold everything is going to dissolve CO2 more readily rather than warm oceans. So you're going on these carbon and albedo feedbacks that exist in the planet system. So, but if what we are doing is increasing CO2 concentrations to a certain point where we have melted off the polar ice caps, okay, which is happening. The Arctic sea ice is going and Greenland ice sheet is going. So now you have to have a much more dramatic shift in the solar radiation reduction that happens from orbital changes in order to be able to have this next ice age come through. So we might be actually changing the chemistry of the atmosphere so dramatically that in order to trigger the next ice age, the orbital variation, orbital parameter variations of the planet of Earth may not be sufficient to push it into the next ice age. So but this is speculative, because there's many things that happen. There are many feedbacks, and even so, 20,000 years from now, what happens? We may not be around to care for it. So the problem is more immediate than these next ice age, which is going to be tens of thousands of years away, even if it can happen.
I got one last question, which is being asked by one of the attendee. So the question is, when it comes to the forecasting part, so what are the challenges in the present scenario when it comes to forecasting in a medium range type of a grid? So generally in the context of India, so the forecasting is not always good or is not considered better. So what is the element which complicates this forecasting? Is it the monsoon, or for the day-to-day to be forecasted?
Well, I think if you're looking at weather forecasts, the medium range or short range forecasts have all improved enormously. One may not think that weather forecasts are good, but compared to where we were, we have come a long way in the last 10, 15 years. Okay, so there's a lot of improvement in the models that are used and the data that goes into these weather forecast models, because you have to constantly observe and input the observed data into your model, which is mathematically, it's what is called the initial value problem, right? Which is what weather forecasting is. Unlike climate, which is a boundary value problem, which is different. So when you look at the processes that affect weather in the short range or in the medium range, different parts of the world are driven by different kinds of forces. In the tropics, what seems to be more important is local boundary conditions, such as the amount of moisture in the soil, for example. Like I said, if you have a wet soil and you have solar radiation coming on it, some of that energy is absorbed and used up in evaporating the moisture that's in the soil. But if you have dry soil, that heats up much faster because all of that absorbed energy is transmitted into sensible heat rather than latent heat. Now, when you have evaporation and soil moisture available, it's going to affect your weather in a different way than when you have a lot of sensible heat but no moisture. So your forecast, therefore, should know quite accurately how much soil moisture and vegetation there is that is going to partition this solar radiation into sensible and latent heats. So this is still something that is hard to do, to estimate the amount of moisture in the soil. There are satellites from which people are trying to do this. So you can imagine if your weather model does not have day-to-day information on how much soil moisture is there in which part of the country or the globe, it is not going to be able to partition that energy correctly and therefore not be able to partition how much evaporation is occurring or water vapor comes into the atmosphere. And all of these are very critical to how your weather unfolds. So to my mind, there's a lot of work that needs to be done in improving the knowledge and the ability to observe and model these things in order to improve forecasting. So while there are some attempts at doing this, it is still in very early stages. And that's where there is a scope for a lot of improvement, in my opinion.
Yeah, so I must say, thank you so much for the wonderful lecture, and all the queries were very well answered. So I'm very happy for having to listen to this lecture, and I again thank you so much. I mean, again thank you for sparing your valuable time for us. I may now request Professor Verma to kindly pronounce the vote of thanks. After that, we can close this session.
Thank you, Professor Sunil. So on behalf of the Department of Physics and also on behalf of the Institute, I sincerely thank Professor Krishna Achyuta Rao for delivering the Institute lecture. I also thank Professor Sunil Krishna for coordinating the lecture. I thank all the participants who joined through WebEx and YouTube Live. And there is one announcement from Institute Lecture Committee. We are aware that Nobel Prize in Physics 2021 was awarded for groundbreaking contribution to our understanding of complex systems, with one half jointly to Syukuro, Manabe, and Klaus Hasselmann for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming, and the other half to Giorgio Parisi for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. Today's Institute lecture by Professor Krishna Achyuta Rao has covered various aspects related to the work done by Syukuro Manabe and Klaus Hasselmann. Very soon, we will have one more Institute lecture highlighting the work done by Giorgio Parisi. The Institute looks forward to your participation in that lecture too. thank you everyone again for making this event successful.
Thank you.
Thank you so much, Professor Rao.
Thank you.
Thank you for giving me the chance. I really appreciate it
pleasure.
and enjoyed it. Thank you.
Okay, so we can close the event now.
Yeah. Yeah, thanks again. Yeah.
You're welcome.